next section. We are starting to get into the fun stuff. Chapter 2 in general is probably one of my least favorite chapters. I really don't like continuity and all of that. But we are getting into derivatives. So this section is going to be a lot of the definitions of derivatives, but then kind of like most things we do in calculus, once we learn the why behind something, we can learn some of the shortcuts that can help us, just like we did with limits. Remember, we started out the long, painful, making the tables, looking what they go to, so we understood the process, and then we figured out what we could and could not do as shortcuts. So that's kind of where we're at with this. So we are going to spend the next probably 2 to 3 days on this. Big thing, we're still talking about tangent lines. That's something we've seen a lot. We know we looked at those back when we were talking about average rate of change, instantaneous rate of change. It's still here, so we know a tangent line is just a line that hits a curve in one spot. So if I look at a graph, and let's say I have something like this. If I am looking right here, I'm going to call that A, so the y value is f of A, whatever you get when you plug A into your equation. And so our tangent line, it looks like this. And we know we had to take another point on that line. Okay, we were trying to find the equation of it. And so we looked at a second point, but we knew that in order to make it as good as possible, it had to get closer to A. So if I call this point X, and its y value f of X. Okay, the slope is y2 minus y1 over x2 minus x1. Change in y over change in x. And if I want that slope to be as accurate as possible, x and a have to get closer and closer and closer to each other. That's why we made tables. And like if we were looking at 2, we would plug in 2.1, 2.01, 2.001 to make those slopes as close together as possible. So we have to do the limit as x is getting closer and closer to a. So that is the slope of the tangent line. The limit as x approaches a, f of x minus f of a over x minus a. That's what we did with all those tables. We can now use what we know about limits to evaluate those, or write equations for tangent lines without first making the whole table. So if I want the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Right, so my points, one point is 1, 1. The other point would just be whatever x is, and the y value of that is the equation, x squared. So to find our slope, we have to do the limit as x gets closer to 1, and we set up our slope, y2 minus y1 over x2 minus x1. And using what we know about limits, how could I evaluate this limit? Those cancel, and now you can plug in your 1. So we have 2. So we have a line with a slope of 2 going through the point 1, 1. So y equals mx plus b. We need to get our b. So y equals m times x plus b. So y-intercept is -1. So equation y equals 2x minus 1. Really not anything we haven't done before. We found the slopes of all those tangent lines. We've written equations of tangent lines. But when we did that, it was back before we really had all of our limit shortcuts. So now we're just pulling those two pieces together. There is a second notation that we sometimes see. So in this, I called my points A and X. Another way to look at it is to say, okay, this point is A plus some amount. So A plus H, and A is just, or H is just some small number. So then this Y value would become F of A plus H. And if those two things are getting closer and closer together, what is H getting closer and closer to? 0. H is the amount we're adding. So it could be as it approaches 0. So this is the second definition. It's still the slope, but now my points are F of A plus H and F of A. But we're looking as H approaches 0. We can use either one. This one is sometimes nicer because the way it turns out when we do your slope with your points, okay, y2 minus y1 over x2 minus x1, what happens on the bottom? Those A's cancel and just leave us with an H. And that can sometimes be nicer for reducing purposes. Sometimes it's easier to cancel a single term off the bottom than multiple terms. So they are equivalent. You can use either one. Algebraically, sometimes this is going to be a little bit easier to work on. Questions there? So let's try using both of these definitions and just kind of seeing how they work out. So we're going to do the same problem twice. First time I went to do the equation line to y equals 3 over x at the point 3, 1 using the second method. So the second one is the limit h approaches 0, f of a plus h minus f of a over h. Okay. What is my a value? 3. So if it helps, you could write out the two-word pairs. Second one, we're going to do 3 plus some amount, 3 plus h, so then the y would be 3 over 3 plus h. So when you set up your slope, f of a plus h minus f of a all over h. Okay, can I just plug in my h right now? No. So, strategy. If I want to, we don't like fraction and a fraction. So if I wanted to get rid of this denominator, what would we multiply by? We could just do the denominator. But, since we can't change the problem, you have to take everything times that. So those cancel and we get 3. Minus, if I distribute my 1, so minus 3, minus h. Did you smile pretty? Mm-hmm. So now what happens? How can I reduce here? And then, a very common issue on the test, if those h's cancel, what is h divided by h? 1. So we get -1 over 3 plus 0. represents what? The slope. Now we need the equation. So we have a point and a slope. So y equals m times x plus b. So our y-intercept is 2. So the tangent line is -1/3 x plus 2. So still not a super short problem, but it is faster than using those big tables to try to find our limit for the slope. Questions on this one? So we are going to repeat this problem. We're going to do the same one again, but this time we're going to use definition 1. So we talked about 2 different definitions. You can use either. I'm just showing you how they both work. So definition 2, that was the a plus h one. Definition 1, if you need to flip back, is when we do the limit as x approaches a, f of x minus f of a over x minus a. What is my a in this problem? 3. Okay, f of x, so if we think about our points, we have 3, 1, the other one would just be x, and then the y is 3 over x. So f of x minus f of a over x minus a. That's what y is equal to from the equation. All right, can I just plug in the 3? Nope. So if I want to work this problem, first thing we have to do is get rid of the fraction in a fraction. So we could do that by multiplying everything on top and bottom by x. So we get 3 minus x over x times x minus 3. Does anything cancel yet? X minus 3 and 3 minus x are very close. What do we have to do to make them cancel? We could factor out a -1. Okay, so if I took out a -1, then I would have a positive x and a -3. Then those cancel. Plug in, we get -1/3. And this, same thing we got on the last one, that is our slope. So then your equation, plug in your point, y equals m times x plus b. So if we add that over, and b is 2. So y equals -1/3 x plus 2. Same equation, just 2 different definitions for getting there. Any questions on that one? Okay, so I'm going to talk just a minute about velocities. We'll do one example of that, and that'll probably be where I stop today. We're going to try to break this up and do a little bit each day. So these were all doing equations of tangent lines. Velocities. We have talked about average and instantaneous velocity. It was on your test yesterday. Average velocity is what? The slope. So in these, if you just did this without the limit, that's the average velocity. When you throw the limit in and look what the slopes are approaching, that is instantaneous. So average velocity is just our slope. Instantaneous velocity is when you add in the limit there. Okay, and technically we could use either definition. I just went with the second. So Average velocity is the slope. Instantaneous velocity is the same thing as the slope of a tangent line. It's when we have the limit. So let's look at one example using that. Suppose that a ball is dropped from the upper observation deck of the CN Tower, which is 450 meters above the ground. I want the velocity of the ball after 5 seconds. Is this an average or an instantaneous? Instantaneous. Instantaneous is a velocity at one point in time. It's not between two values, just at one point. All right, so I'm telling you to use this equation. Okay, this gives us how far it has traveled. So, if we want to find our velocity, we need to do the limit. Okay, we can use either definition. Let's just do the second one. So that's the limit. H approaches 0. F of A plus H minus F of A all over H. Okay, what is my A in this problem? 5. So that would be F of 5 plus H minus F of 5 divided by H. So 5 plus H, if I put that in for my equation, I get 4.9 times 5 plus H squared minus F of 5 would be 4.9 times 5 squared. Okay, and again, this part is from my equation. I just plug those things in for my t. So now we have to multiply. Can I square and distribute my 4.9 at the same time? So 5 times 5 would be 25 times 4.9 gives me 122.5. Plus 5h and plus 5h would be 10h times 4.9 would give us 49h. Plus h squared, so plus 4.9h squared, so that's the first piece. Minus 4.9 times 5 squared is 122.5 all over h. What happens? So we have 49h. So now what? Okay, we can take 1h out of everything. So we have the limit as h approaches 0, 4.9 plus, or sorry, 49 plus 4.9h. So if you plug in a 0, we get 49 meters per second for the velocity. So we found that after 5 seconds, this is our velocity.
Oh, thank you.
Is that okay? Second thing, how fast is the ball traveling when it hits the ground? Okay. So what would we have to do? So, yes, if it hits the ground at 0, the equation that was given is a measure of how far it has traveled. So if it started at 450 feet and then it got all the way to 0, how far did it travel overall? 450. So because the equation given was distance traveled, we would have to set that equal to our equation. So if you divide the 4.9, it's not real pretty. And then how do you get rid of a square? Square root. Normally you do plus and minus, but we know you can't have a negative time. So what this tells me is that t equals 9.58. And that's when it hits the ground. So it hits the ground after 9.58 seconds. But my question wasn't when it hits the ground, it was how fast it was going. So what am I asking you to do? The speed, the velocity. Same thing we just did, except this time my A is 9.58. Alright, so not pretty, but we can do it. So if I FOIL and distribute my 4.9 to 9.58 squared times 4.9 9.58h plus 9.58h times 4.9. Do you guys know where I'm getting my numbers? Plus h times 4.9. Pretty ugly. But what happens now? Those cancel. Then, after those cancel, we can take an h out of everything. So you're left with 93.884 plus 4.9 times 0. And we get our new velocity. Questions there? So we are going to stop for today. The big thing on this, guys, it's a lot of algebra. Don't try to skip too many steps. That's when we make mistakes. We drop negatives, we, do h divided by h and call it 0 instead of 1. So just make sure you're not skipping too many steps. The homework from this section, we are definitely not all the way through, so it won't be collected for a few days, but you could do probably up through problem 13.